All right, hello students. So today we are going to talk about Taylor's formula with the remainder. So really quickly, let me hide some of this. Okay, here's the Taylor's theorem. If you have a function and its first n plus 1 derivatives are continuous on the interval of x minus a, which is what you're centered around, less than r, then for each x in this interval, you know that this is your Taylor formula, okay? But if you go up to n, then here, n plus 1, which will be all these other terms here, will be considered your remainder. So that part right there is called the Lagrange remainder. So you know there's an infinite number of terms in your Taylor series. So essentially, if you are using a Taylor polynomial n, which would be basically this first part right here, plus the rest of your Taylor series, that would equal your f of x. So this is your Taylor polynomial, and this is the rest of it, okay? Now, this part right here is the error that you would get when using this polynomial to approximate your f of x. So let's say if you are approximating f of x, you know that there is an infinite number of terms. So let's say you only take a polynomial of up to 3 terms. So then the rest of it would be your remainder, okay? So now that's what your r of nx represents, okay? So now what we like to do sometimes is find out, well, how off is our Taylor polynomial? What is the maximum that it can be off? Okay, so that would be our Lagrange error-bound formula, okay? Which is all of this, okay? So let me explain to you what it is, okay? If you're using a polynomial of n degree, okay, then the error that you would experience would be less than the maximum value from this formula right here, okay? So if I said let's use a third degree, then my n is 3. So therefore, this would be the fourth derivative of c, which I will explain in a minute, divided by 4 factorial, x minus a to the 4th power, okay? Now let's talk about a little bit of some of these terms, okay? First off, c would be an x value that we may or may not find, but c, that would always be in between your x and your a. Now what is your x and your a? Your a is the x-coordinate that you are centered about, okay? So that comes from our Taylor polynomial. We are centered about a, okay? Now, your x is the x-coordinate at which we are using our f of x, and we're approximating that x-coordinate. So you'll see in our examples how we label our x, okay? Now, what we do, how do we get this maximum? This maximum is determined by looking at the n plus 1 derivative and looking on this interval between x and a, or a to x, depending on which value is greater, and then finding out what is, now this is a y value, okay? There is a c, but this is a y value, okay, where our c is in between these two x coordinates. We want to find the largest y value of this n plus 1 derivative. And we will take that and we will substitute that large y value right there, okay? So, for example, let's do from that worksheet that I gave you, example 13. Okay, so let's look at example 13 really quickly. Okay, it says let f be a function given by this. And let p of x be the third degree Taylor polynomial about f of x at x equal to 0. Show that the Lagrange error bound for f of 1/3, so I'm approximating f of 1/3, is less than this. Okay, so here we go. We're showing that this is less than 0.01. Okay, and this is what my f of x is. Okay, and they said about x equal to 0, which in other words is a Maclaurin series. All right, but what they're really concerned about is the Lagrange error bound. So that is this formula. Okay, now it is important now from this problem to understand what is our x and what is our a. If I said f of x, then that means my x is 1/3. And I'm saying about x equal to a, so that means x equal to 0 is our a. So that's how I determine my x and my a. Okay, and this is the formula that I had from the beginning. Okay, now what I'm going to do is I'm going to input it according to the values that I'm giving. So I'm saying, okay, I have a polynomial, a third degree Taylor polynomial. What would be my maximum error if I use that to approximate f of 1/3? So what you do is you input all the values into your formula. Your x is 1/3, the maximum f. Now this is 3, so 3 plus 1, that is 4. So the fourth derivative at c divided by 4 factorial, and then my x is 1/3 minus my a, so that is 0 to the fourth. Now, off to the side, you want to work it out, and hopefully I got the right answer, that my fourth derivative ended up being this. Okay, so what I need to do is I need to graph this. Okay, so I graph this. So here is my formula, which if you look there, there is that expression. Okay, now this is cosine. So what I did is, darn it. When I drew this, I made sure that my viewing window was between 0 and 1/3, okay, between my a and my x. So my viewing window, the x coordinates, are in between 0 and 1/3. And what do I know about cosine? That the highest y value is 16 and the lowest y value is negative 16. So I made that my viewing window, okay? And so now I look at this graph and I go, okay, on this interval of 0 to 1/3, what is the highest y value? So I look at this, and the highest y value is that y-intercept right there. So that is what I do. I go, okay, so then this maximum occurs when c is 0. Okay, and I want to find out what that is. So you use your calculator skills and you find out what that y-intercept is. Sometimes it's a y-intercept, sometimes it's something else. It might be a point way up here, but it is the highest y value on this viewing window. Okay, then you input all of that into your formula. So now I get rid of that max because this is the maximum. I input that and I calculate it, and that does end up being less than 1/100. Okay, and that's how you do example 13.